So, what is a tangent space? Now, tangent space represents a coordinate system, basically, which is two axes of this coordinate system are on the tangent plane of the surface. So, what is the tangent plane of the surface? Now, for an object like a plane, it's easy, right? So, this is the, let's take the front face. This is the tangent plane. Okay, let's take the top face. This is the tangent plane. So the plane that is tangent to the surface. And for the right face, you can find it, right? Now, as you know, to define a space, we use three vectors. So let's take the front face. So one vector can be like this. Okay, we call this vector the tangent vector on the plane. Okay, this second vector is going to be orthogonal to the first vector. That's called a bitangent. Okay, so T is a tangent vector, and B, okay, is the bitangent vector. Okay, so these are typically orthogonal to each other. So we have a tangent vector, bitangent vector, and the third vector in this space is the normal vector. Normal, okay, so each of them are vectors. TBN. So this space is typically known as TBN space. Okay, tangent, bitangent, normal. These three vectors are perpendicular to each other. Although, for correctness, it should be said that the tangent and bitangent do not necessarily have to be perpendicular to each other, but generally they are in computer graphics. So basically, these vectors form a space on the point for every point on the surface. Okay, so the TB vectors form a plane, the tangent plane are on the tangent plane of the surface, and the N vector is pointing in the normal direction. Now, the tangent plane can be defined for any type of surface, including like the spheres that we have. So let's take this point, for example, point P on the sphere. What we can do is we can compute the tangent plane. Okay, so this is, let's say, the tangent plane. Two vectors, we can have T and B vectors, and this is the surface normal. Okay, so the tangent plane is defined, and as you can see, for the sphere, the tangent the tangent plane is going to be different for every point. But for a planar object like a cube, the tangent plane can be the same as long as we are on the same polygon. When you come to here, the tangent plane is going to change. Now, why is this tangent space important for normal mapping? Now, the reason is the normal map texture. Okay, this is the normal map texture. The normal map texture is meaningful with respect to the tangent space of the surface. What does it mean? So, as you know, the normal map, we can associate a coordinate system with this. Okay, so let's say this is the U direction. Okay, and let's say this is the V direction. Okay, U direction, V direction. And at every point, we have a normal value in the normal map, right? Now, the normal value at every point, okay, so let's say we have a normal that's kind of like pointing like this. Okay, so the normal value. Now, let's say the normal is, maybe I can illustrate it better with the board marker. So let's say the normal is pointing like this, okay? So imagine this board as the texture map, and the normal is pointing like that. So what does it mean? It means that the normal is pointing towards the U direction. Okay, so it's pointing towards the U direction. Or if it is pointing like that, it is pointing, the normal is pointing towards the U and V direction. If it is pointing like this, it's pointing, the normal is pointing towards the u, but negative v direction, and so on. Okay? So if we match this space here on the normal map with the tangent space on the surface, okay, we are going to reorient the normal. So in this example, we are saying that the normal is pointing towards the u direction. Okay, so let's say the normal is pointing towards the u direction. What does it mean? When I take the normal from this point and put it on my surface at this point, the normal is going to point towards the t direction. Okay, so this is the normal. Let's call it m prime, the normal coming from here, n prime. Okay, so this way, say in the same way, let's say I'm trying to apply the normal map for this point. Okay, now this is the t, this is the b, and this is the normal, geometric normal. Okay, the TBN coordinate system. Now when I want to take a normal from the normal map, let's say I want to take this normal here. Okay, so for this normal from here I want to take, so I know u is like that, okay, v is like that. So now imagine that the normal is pointing along the okay, so negative u and negative v direction, the normal in the texture. So when I map this space, when I match this space with this space, I will know that then the n prime is also pointing kind of like that. Okay, so you can see now, imagine the sphere case. In the sphere, the same normal, the tangent plane will be different. So this tangent plane, imagine we have a different tangent plane here at this point. Okay, for this point P, you have a different tangent plane, T, B, N. Okay, so we have a different tangent plane here. The normal that you select, imagine that we were selecting the same normal. Okay, so imagine we are selecting this normal, pointing towards u. Okay, so in this case, the normal that I get from the normal map is going to kind of like point like that, and for here it's going to point like that. So this is m prime, m prime. Now what I mean by this is that the same normal value in the normal map can actually result in pointing to different directions on the object. How? It's because we will be mapping the UV system on the texture, on the normal map texture, with the tangent plane on the object.